Okay, welcome back again. Okay, all we're going to continue with now is session 3. Okay, so I don't need to do a lot of talking here in on this case because it's a continuation from session 1, session 2. We're now in session 3. Okay, now here all I'm showing you here now is the outcome that I expect you to be able to know. Okay, just make sure we get it all in. Okay, yes, we have. Good. And again, briefly, what we were looking at previously, and you remember we look at this in session 1. Okay, just go back, make sure we can get it all in. Okay. Okay. Right, centers of gravity. Now, center of gravity means that something is stable, it doesn't fall over. Okay, so you can see your center of gravity is here at this point. Center of gravity is at that point there. Okay, right, and you can read that for yourselves. You don't need me to be reading this to you at all. Okay. And again, lesson for shapes, you can see the center of gravity will be here, okay, at this central point. The center of gravity affects the stability of an object. And here we have an object with a high center of gravity, like a tower or scaffold, cannot tip very far before it will topple over. Okay. Usually, the lower the center of gravity, the more stable something is. So, in short term, the higher you go up, the more support you will need to support that structure in order to ensure that it retains a center of gravity. Okay. If something does not have a good center of gravity, it will topple over. It is as simple as that. Okay. Intersection points. Okay. Now, to find the center of gravity of an object, you can draw a line from all of the outer points, and the point where they all meet is the intersection point, or point of the center of gravity. And here, all they've done here is just simply draw a line and pick up your center of gravity. Sections, rectangular, and so forth. Now, you can read that for yourself. You don't need me to read that to you. So let's make sure we can get it all in frame. Okay. Now, this is what happens when we do not have a good center of gravity. This is where a body remains in a particular state until an external force acts upon it or causes it to get out of balance. Now, this is called an equilibrium. Okay. And the equilibrium is when something is perfectly balanced and it will stand upright. But the moment you apply a force and you disturb that equilibrium, then that structure will fall over. And you can see that equilibrium, stable, unstable equilibrium, and it will collapse. Okay, simple as that. Now, turning moments. Now, turning moments, another word for turning moment is torque. Torque is the turning force applied to an object. So you can see that here, that The force required to turn this nut, let's suppose that spanner is 2 feet, for instance, long, and it will take a certain force to turn that nut, to loosen it off. Okay? Now if I made the spanner 4 feet long, I would therefore reduce the force that I need to apply to the spanner to loosen the nut. So therefore, if I move the spanner up 3 inches, I may only need to move it 1 inch if I extend the spanner's length. Therefore, it gives me a more potential torque to apply to the nut to loosen it. Okay? Thank you. And here we're just extending that further. Okay? Torque is T. Okay? So you can see that we are moving the spanner upwards, but by making that longer, we can apply less force to do the same work. Okay. Mechanical advantage. Mechanical advantage is when we use a tool or machine to do some work for us, for example, a winch or jack. Mechanical advantage is the ratio of load to effort applied. Mechanical advantage, okay, equals load over effort. That should be over. It's just distorted. Mechanical advantage equals load over effort. Okay, that's my line there. It's okay. It tends to go out of sync when I make it larger. Okay, but that's to make sure you can see that. Okay, so that there is M. Mechanical advantage equals load over effort. Okay. And again, here we have the load measured in newtons as well as effort. Therefore, there are no units for mechanical advantage. Okay. The larger the mechanical advantage, the easier it is to move a load. As I was speaking in regards to the spanner, if I make my spanner longer, then the nut will undo easier with less effort. Okay. Now here we have velocity and ratio. Okay. Velocity ratio is the ratio of distance moved by the effort applied to the distance moved by the load. Velocity ratio equals distance moved by effort over distance moved by load. Okay. So the distance, like you may move 1 meter or 6 inches, we should then call the load to move certain lengths depending upon your applied force. And again, there are no units for this. Now, work done. Work is done whenever a force is applied to an object, causing it to move or deform. The amount of work depends on the amount of force being applied and the distance that object moves. Okay. Just trying to make sure that you can see the green. Okay. In full view. Okay, let's come back a little bit. Okay. Right, now, symbol for work is W and the unit is a joule. Energy and work are related. Energy is a capacity to do work. Work equals W equals force times distance. W equals work done or energy. F equals force in newtons. D equals distance in meters. Okay. Now again, you need to do additional reading for yourselves. Check and double check. Look at your work, do the calculations, work them out for yourselves. Okay. And here we have power. Power is the rate at which work is done. Once we introduce the term rate, we are dealing with time. The symbol for power is P and the unit is the watt. There are two formulas for mechanical power. The basic one is P equals W over T. P equals power in watts. W equals work done in newtons, meters or joules. T is time in seconds. Excuse the slight warping of my symbols. Okay. Now this part is very important. Efficiency. Efficiency is a ratio. It compares what goes in with what goes out and gives us some idea of the losses or waste. Now, let's take a transformer for instance. We need a transformer to be highly efficient, so we get out near enough what we put in. And most transformers is about 98% efficient. Okay, 2% you'll lose in heat anyway, so one form or another. Now, if efficiency is ratio of power or energy into power or energy out, and this is your efficiency formula. Remember that symbol. I call it a little n equals energy out times 100, called, you're dealing with percentage in regards to efficiency. Okay. And that is your formula to be applied. Now remember, you may need to transpose this formula in some cases, okay, depending upon the information you have been given. If we didn't multiply by 100, we would get the answer per unit instead of a percentage. Okay. Okay, that seems to be it. Thank you. Okay. End of session 3. Okay. Thank you. Have a good day. Bye bye.